Hello everyone. In this video, I will introduce our paper, ReMoS, Reducing Defect Inheritance in Transfer Learning via Relevant Model Slicing. I am Ziqi Zhang from Peking University. Software reuse is a common practice for software engineers. The easiest reuse approach is copy-pasting a piece of code and make slight change to the copied code. Importing third-party libraries is another common practice. Due to the flourish of open source community, there are enormous libraries available for software developers, such as deep learning libraries, Android development libraries, Java libraries, and iOS development libraries. Class inheritance is one of the primary characteristics of object-oriented programming. It enables the developers to reuse, extend, and modify the behavior of old classes. Class inheritance reduces the repetitive work of implementing basic functions for every new classes. These years, with the rising of artificial intelligence, the DNN models are called Software 2.0. DNN model reuse become a new type of software reuse and is widely used by DNN model developers. This model reuse is also called transfer learning. A typical pipeline of transfer learning is as follows. First, it needs a large company or organization with extensive engineers and computation resources. The company collects and annotates large-scale diverse dataset. This dataset is used to train a complex general DNN model. To broaden the impact and facilitate other developers, the model owner updates the trained model on the internet. Popular platforms include PyTorch Hub, TensorFlow Hub, and GitHub. Then, an individual developer wants to reuse the model and downloads it from the internet. She then prepares a small-scale, task-specific dataset and fine-tunes the model with this dataset. The final model is a specialized DNN that can only perform certain tasks, such as face recognition, question answering, and car detection. In the pre-mentioned pipeline, the general DNN is often called the teacher model. The teacher is trained by a large-scale dataset to complete complex tasks. For example, a teacher model can be trained on ImageNet with 1,000 classes and 14 million samples. The specialized model is called the student model. The student is fine-tuned on small-scale dataset to complete simple tasks. The student model trained via transfer learning has high performance, and the teacher model has been trained by enormous data. Besides, the student model converges fast and spends less time to train. The student owner only has to collect a small amount of data to train the model. Transfer learning saves much effort for the individual developers. Despite the great convenience of software reuse, the vulnerability propagation of the reused software is one of the most concerning issues. Developers are often unaware or unable to eliminate the vulnerabilities in the reused code, which may lead to unexpected consequences. One example is the famous Heartbleed bug in the OpenSSL cryptographic library. OpenSSL is a widely used transport layer security protocol, and the Heartbleed bug was caused by improper input validation. Normally, the client asks the server to send a four-letter word, bird, and the server replies to the word bird. But if the bug is exploited. The client tricks the server to send a 500-letter word bird without input validation. The server replies to the word bird and hundreds of memory data after the word, including secret keys and passwords. The seriousness of heartbleed bug comes from the wide usage of the OpenSSL library. As a basic TLS protocol, OpenSSL is used nearly all the Internet communication softwares. Thus, the heartbleed bug may threat the website's secret digital documents that transmit through the Internet. Instant message applications such as Facebook, Line, and Skype, and VPNs that are used inside companies. Surprisingly, 5 years after the bug fix was released, there are still about 1 million vulnerable devices in the world. Similar to traditional software reuse, transfer learning may also inherit defects. The teacher may inevitably contain defects. Thus, the developers download a defective model. The fine-tuned student model contains similar defects. We summarized two major defects: causative defects and exploratory defects. In this work, we define the DNA defects as the deviation of the actual and expected output of a DNA model produced by certain input samples. We mainly focus on two types of defects: adversarial samples and backdoor. Adversarial samples are generated by adding carefully generated noise to the input to mislead the DNA model. Backdoor samples are generated by attaching special triggers to the input. Adversarial vulnerability is a representative of exploratory defect. To use this defect, the attacker first downloads the teacher model as the developer does. Then he carefully analyzes the model and finds bugs of the teacher DNA. These bugs may be inherited by the student and be used to attack the student application. DNA backdoor is a typical example of causative defect. In this scenario, the attacker intentionally poisons the training data. Then, the trained teacher model contains some special backdoor. After the developer fine-tunes the student model, the backdoor remains and becomes a threat to the downstream application. The defect inheritance in the software reuse and model reuse is similar. During model reuse, developers fine-tune the public teacher model to train the student model. For software reuse, developers import the public code library to develop the downstream applications. The attacker can download the public teacher model and code library, analyzes the vulnerabilities, and poses threat to the student model and downstream applications. To analyze the threat of defect inheritance in transfer learning, we surveyed prior literatures and summarized several potential defects. The literatures include both CV and NLP tasks, covering adversarial vulnerabilities and backdoors. The experimental results show that the defect inheritance rate ranges from 52% to 97%, meaning that the defect inheritance is a real threat to DNA model reuse. The root cause of DNA defect inheritance is that the student has a similar decision boundary as the teacher model. In the figure, the yellow dashed line represents a perfect decision boundary. The blue circles and the green triangles are samples from two classes. The black curve represents the decision boundary of the model. The samples in red represent the model defects. As the student model is fine-tuned from the teacher, the decision boundary of the student is only slightly different from the teacher. Although there are some fixed defects, there are plenty of inherited defects that are misclassified by the student. The defender score is fourfold: effectiveness, accuracy, efficiency, and utility. Effectiveness means that the inherited defects should be reduced. Accuracy and efficiency means that the student model should not sacrifice model performance and training time. Utility means that the proposed technique should be scalable to various tasks and model architectures. The Venn diagram shows the goal of mitigating defect inheritance. For conventional transfer learning, the teacher and the student share much knowledge, including both student-related knowledge and defect-related knowledge. We aim to compress the shared knowledge as much as possible, so that the shared knowledge only contains mostly the student-related knowledge and excludes the unrelated knowledge. To reduce the defect inheritance problem, we propose to use relevant model slicing, which is also called ReMoS. ReMoS is motivated from relevant slicing, which computes the statements that have the potential to influence the target variable. The figures shows an example. The code snippet contains a potential defect. If the input B is 0, a divide by 0 error may occur at line 8. Directly reusing this code snippet will definitely inherit this defect. If we know the input domain of the downstream applications, we can only reuse the relevant slice and mitigate inherited defects. For example, if the input domain is A is less than 1, we can select a criterion and slice the relevant parts. The defective statement is excluded by the relevant slice. Thus, the inherited defect is mitigated. Similar to relevant slicing for programs, the relevant slicing for DNN aims to extract the weight subset that is more relevant to the student dataset. As the teacher model contains general knowledge, it is possible to select different weight subset for different student tasks, thus minimize the possible inheritable knowledge. ReMoS consists of 4 stages. The first stage is coverage frequency profiling. This stage uses the student dataset to compute the coverage frequency of each weight, which represents the relevance to the student task. The second step computes a score for each weight based on the static information of the teacher model and the dynamic coverage information on the student task. The third step identifies the relevant slices based on the computed ordinal scores. The last step uses the student dataset to fine-tune the relevant slice, as the conventional transfer learning does. We did a comprehensive study to evaluate ReMoS. The evaluation goals include defect mitigation effectiveness, generalizability, efficiency, and interpretability. The experimental setting includes 4 DNA models, 7 DNA defects, and 8 datasets. We implemented various DNA defects. Penultimate layer-guided adversarial vulnerability is a special attack tailored for transfer learning. it targets the penultimate neurons of the DNA model. The second type of defect is neuron coverage-guided adversarial vulnerability. It is adopted from the prior literatures of DNA testing. This attack targets all the internal neurons, and we implemented 3 different coverages and 3 strategies. For the backdoor, we implemented data poisoning. The attacker points the training dataset and injects backdoor in the model. The last defect is weight poisoning backdoor attack. The attacker directly manipulates the model to inject backdoor. We then display some evaluation results. For neuron coverage-guided adversarial vulnerability, ReMoS eliminates averagely 63% of the inherited defects. For the NLP backdoor, ReMoS eliminates 50% data poisoning defects and 61% weight poisoning defects. To summarize, in this paper, we found that the popular DNA model reuse faces defect inheritance problem, like traditional software reuse. We identified 2 possible inheritable defects, adversarial vulnerability and DNA backdoor. The defect inheritance problem can be mitigated by only reusing the relevant model slice, instead of the whole DNA model. We propose ReMoS, a relevant model slicing technique that can mitigate over 60% CVIP defects and 40% NLP defects.